This meeting is being recorded.
In section 15.2, we're going to look a little bit more in detail about the process of proton nuclear magnetic resonance spectroscopy. And what we see here is, again, NMR will require both a strong magnetic field, so that's commonly referenced as this B sub 0 here, and also radio wave energy. So this is, again, comparable to the infrared light or radiation that we used with IR spectroscopy. Now we're going to utilize radio waves. We can see here that there's two different delta E values given here. And these are dependent on the strength of the external magnetic field that is applied. So here we have a lower strength, a 1.41 Tesla magnetic field, and we can see that the energy gap between our alpha and beta state is this amount here, whatever that energy difference is. Whereas we have a greater energy difference when we have a greater magnetic field applied. So we have, again, our alpha and beta state and that greater difference between them. So what we're going to see is that we can use different magnetic fields, different energies to create different energy gaps, but they're always going to be related to one another as far as the ratio goes. So again, we create this strong magnetic field, and this is generally done utilizing a high current being passed through a very low temperature. So you can see here approximately 4 Kelvin. So generally they need cooling gases and a variety of expensive equipment to keep this type of magnetic field generated. And then the current utilizes, or rather the spectrometer utilizes this pulsed Fourier transform technique, and it generates all the relevant wavelengths that are used to excite or energize our sample. So each of the atoms is then excited, then relaxes, and we see the emission spectrum. We see the emission of energy, and this is recorded using what's referred to as free induction decay. But again, you will not need to know all the details of the inner workings of the spectroscopy as far as utilization of this free induction decay and the Fourier transform mathematical calculation that's involved to convert these signals into what we see generated on the spectra. So before we analyze our NMR sample, there is something that you would need to know about here, that these samples will need to be prepared in these small tubes, these glass tubes. They can be prepared neat. So that means without any type of liquid or solvent utilized. Or if we do need a liquid solution to be utilized, we can use what's called a deuterated solvent. So if you recall, I refer to H1 as protium, but when we have a hydrogen that is deuterated, it will have a mass of 2. So any solvents that need to be used, we can use deuterated solvents. That way, the protons will not respond to our NMR and give us false signals or signals specifically from the solvent. So again, this is what that deuterated means, the heavier hydrogen. So we place these into those small NMR tubes. The sample is then placed in a magnetic field, and we spin the tube. And then we find the average of the magnetic field that is generated. And from there, we can see this is a general setup. So we have our deuterated solvents utilized. So again, no protons. These will have to be H2, so heavy hydrogen. And then the sample is collected at room temperature, but we do use that supercooled magnet. So liquid helium is one of those gases that can be used to cool our magnet. So therefore, we can generate the right strength of magnetic field to analyze our sample. And again, you don't need to know much about the actual data transformation here, this Fourier transformation and the mathematical analyses that are done. So we will utilize this knowledge here that we covered in section 15.2 when we talk about the generation of the spectra in our next section, 15.3.